Hi, good evening all. This is Vishal Singhal from Shellstat. Thank you for joining the webinar. Hope all of you are keeping safe and sound. So today we have Mr. Rameshbabu Lakshmanan, one of our researchers in Shellstat AI Lab. He's taking us through this NLP's technique on POS tagging with Skipgram. Uh, so I'll hand it over to Ramesh now.
Thank you, Vishal. Welcome all. Good evening.
So you can share your screen now, Ramesh.
Sure, Vishal. Are you able to see my screen?
Yes.
Okay.
Go ahead.
Okay. So today we are in one of the exciting topics, the current trend, which is NLP, which stands for Natural Language Processing. So myself, Rameshbabu Lakshmanan, I am a part of a self-taught AI researcher. I have 14 plus years of overall experience in IT field, primarily working in banking services with experiences ranging from investment banking to the retail banking domain. So I am currently a project manager, and I take care of product management, scope management, financial management, and we are slowly switching into the AI to understand to how best to use the AI in the AI and the deep learning models in the financial industry. I am also a marathon runner, having completed multiple 10Ks and 2 off marathons. Just an additional fact about me. So getting into this webinar, which is POS. Okay, I will just briefly explain. Today we are going to deal with part of speech, how we are going to uh, uh, arrive at the part of speech on the basis of Skipgram model. So I'll just quickly jump into the problem statement. This is the agenda, which is where we will be covering the problem statement, and we will explain briefly what does the cost of speech POS stand for, and what does word embeddings mean, and word to vector, which is primarily used for performing word embedding over here, and finally the neural network architecture that will be used to determine the POS. Now you can stop me at any point of time and ask me questions if you have any doubts. Otherwise, I will just keep continuing. So this is the problem statement that we are going to focus on now. We are going to identify the part of speech tags for the given corpus. The solution that we have taken up to identify the part of speech is first to create the word embedding matrix using word to vector, and train the dense neural network to identify the part of speech. Then we will perform the POS tag and measure the accuracy. Finally, we would also see how we are improving the accuracy by building a context-dependent model. So the reference for this is taken up from Cambridge Analytics assignments. You can Google it out and find out. The problem statement is inspired from there. And the data sets that I have used are the standard NLTK libraries, natural language toolkit libraries, which are there within the Python code. Okay. Just quickly moving on, POS. POS stands for part of speech. So POS is not a new term. It's neither a machine learning or nor a deep learning term. It has been there in information retrieval context since quite some time. So part of speech is nothing but the words that we speak, the sentences that we construct. Each and every word can be tagged to a specific part of speech. We would have learned this all in our school days, where we would identify the subject, verb, object, and then we will again identify the noun, principle. We will identify the tense. So all these can be called as part of speech, though in schools we just dissected the sentences in broad terms. But here in NLP, we can actually tag each and every word with the given POS tag. There are certain, I have just listed down here few of the POS tags. This is called a universal tag set. For instance, adjective, adposition, adverb, conjunction, determiner, noun, numeral, particle, all of these are called POS tags. And certain examples of the POS tags are also given over here. There are standard POS taggers available online, which can be used to find out the tags of each and every word, provided we give the right sentence. So, for example, if I give a specific sentence such as John likes the blue house at the end of the street, and I use the NLP Stanford tagger, what I got is the tags over here, noun. Each of them, I have represented each of them with their respective colors. For instance, I used noun, and I mean brown color for noun, verbs, blue color. So all these are different tags. So why do we want to tag the given sentences or a given word? This can be used to identify the pattern. We will be able to derive some meaningful information out of the tags, and can be used as a feature to perform probably a text mining or text classification at a later stage. So this is one useful information available in the text corpus that is being harnessed by the deep learning networks to arrive at a lot of different stuff such as text mining, classification, text analysis, fraud detection, and so many different things. So this is just a sample of POS, what I have described here. And moving on, we want what we want to do. We want actually to represent the text right in the machines. So machines can understand only the numbers, as we all know. So one option for me is, for instance, if I have a sentence, I ate the orange for the breakfast, right? If I want to represent this as a number to a machine, probably I can go for a very easy encoding, which is integer encoding, wherein I will give some unique values for each of the words, right? So if you see here, I have given 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7. So there are 7 words. I have integer encoded only 6 words because there are only 6 unique vocabularies, right? That is repeated twice. To feed it further into the machine, we can actually use one-hot encoding. Right, which is a typical traditional way to encode the integers. So if I use one-hot encoding, I can go with this particular mechanism where I just represent the position of the specific words in this specific dimension. So if there are like 6 unique words, I will take some 6-dimension numbers, and I can just say that position. If I say 1 as a first position, this will stand for I. If I make 1 as the second position, to stand for 8. So in this way, I have uniquely encoded all these words, right? So if all the encoding is already available, what is the problem? Right, so we have the encoding already available, so we can use this for further processing in our machine learning or deep learning. But there is a big problem over here, because if you see here, right, it first of all, it requires a big dimension. I have used only 6 words, and if you see, there are like 6 dimensions required to represent these words. And our vocabulary is not limited to 6 words. We speak numerous vocabulary, right? There are more than 10 million words probably in any language if you take, and if you have to represent the whole vocabulary, you may have to go for 10 million dimensions. Is it really possible? No, right? So in order to reduce the computational complexity, as well to derive some meaningful interpretation out of these words, right? So if I read 1 followed by multiple zeros, and 0 followed by 1, and then multiple zeros, I am not able to make any semantic or synthetic meaning out of this, right? For instance, how are I and 8 related? These numbers are not, or the encodings are not giving me any sense out of it. So I need to go for a better representation. So how do we go for a better representation? So we go for word embeddings. So word embeddings, what they primarily do is they take the sparse matrix. This is what we call as a sparse representation, where there is only one value followed by multiple numerous zeros, where we are not encoding any of the meaningful information. We will primarily be converting into a dense vectors, where we will be having a continuous representation. So again, word embeddings are also not new. We have a lot of different techniques to do word embeddings. such as count vectorizer, TF IDF vectorizer, hashing vectorizer, word to vector, which has come from Google, and GLOW, which has come from Stanford. And there could be also additional other techniques for word embeddings, but I have just represented only the major ones which are being used. And as we speak, the word embedding techniques continue to evolve. There is a fast text. There are also other embedding techniques which are later available and which are available latest in the market. So the NLP field is continuously evolving. So the word embedding representation as well. So every now and then a new algorithm or the existing algorithm is being updated or changed so as to make the word embeddings meaningful. Now, in this specific page, I will just briefly touch upon how the word embeddings really work. This is how the word embedding really works. For instance, if you have sequence of different words, for instance, cat, kitten, dog, houses, right? If we have to use one-hot encoding for representing these words, probably we may have to go with 0, 1, 0, 0, 1, 0, 0, 1, 1, 0, 0, right? Like that. We will use 4 dimensions to represent this. But they don't give any meaningful sense. Now, how do we convert into how do we actually see the word embeddings? How do we visualize the word embeddings? This is how it will be. For instance, there are certain common the way how you can interpret the word embeddings are all the words are connected by certain meaningful representation. For instance, living being, feline, human, gender, royalty, verb, plural, right? Let us say these are the different dimensions, and we can represent different words with different values given for each of the dimensions, and still we can get the same still we can get a different representations. For instance, cat can be a 0.6 for living being, and it is more of a feline, which is 0.9. It is less of a human, which is 0.1. Whereas if you go for dog, it is again more of a living being, but it is less of a feline, which is minus 0. Ways how you can represent each of these words, and you can get a meaningful interpretation. So what the word embeddings primarily do is, once you feed in the corpora text, right, which has all these words over here, we get different representations for each of them, which is a vector space. And finally, you can actually what you can do is you can actually embed it into a dimension which you want. Typically, people go for like 100 to 300 dimensions, and since we cannot visualize the entire word embeddings in the higher dimensions, we would actually view it in the lower dimensions by using other techniques. So what I have shown here is just projecting the 7 dimensions to 2 dimensions over here. And if you see here the vector space, right, you see the cat and kitten are positioned together, dog is positioned differently, and house is in far apart. So there are certain understandings that you can make out of this embeddings. For instance, cat and kitten are similar probably, right? And then if you see the direction also matters over here, right? Dog and the cat family, probably from dog you can actually move to cat with some representations.
Ramesh, you're not audible.
Okay, sorry, I got into mute. Okay, and you can actually see that a man and the woman can be grouped together, king and the queen can be together, and there is a way you can move from man to woman. And the similar way you can move from king to queen. Probably if you add, say, king plus 1, it will move to queen. Man plus 1 will move to woman. So there are certain meaningful mathematical operations that we can do once we convert the text into the word embeddings. That is primarily the concept. This is nothing but the same representation, but just representing in terms of vectors, where we can clearly see that king is represented over here and queen is represented over here. And if you want to move from king to queen, actually you can do some mathematical operations and move it over here once we have this kind of a vector space. What you see in figure 3 is a 2D representation, which I would also show via code. how we arrived at this particular representation. But finally, if you see the word embeddings, right, at a higher dimensional representation is being projected into lower dimensions. These are the different clusters. For instance, if this embedding has been trained, if the words have been trained with a specific embedding technique, you might probably see this particular cluster represents body parts, this particular represents food. You can actually name it because this cluster represents travel, this represents feeling. So once you, depending upon the corporate text that you actually feed in, the word embedding technique takes all the input words and then create some meaningful representation called as a word embedding, where you will see the related words are clustered. And once the related words are clustered together, we can apply a lot of mathematical operations and derive some text meaningful interpretations such as text analysis and classification as such. Okay. So we are coming to the meat of the presentation, which is word to vector. So so far we briefly touched upon what is one-hot word representation, what is a word embedding technique, how the words are represented by vectors by means of word embedding techniques. Now, right, as I said, there are different means of arriving at word embeddings, and one of the method to perform word embeddings is word to vector. And word to vector is actually coming from GenSim library. So we have to import the GenSim package, and GenSim package has got word to vector implemented. It has also got the other fast text mode also implemented. But primarily, I have taken up word to vector, and within word to vector, I have taken up specifically the Skipgram model to actually implement to solve our problem. So within word to vector, there are two different ways how you can actually come up with the word embeddings. That is, one is continuous bag of words. The other one is Skipgram model. And in terms of Skipgram model and the continuous bag of words, there is one difference. For continuous bag of words, you give input as a context phrase and output as target word, and in Skipgram, you give input as target word and output as context word. So I will explain you what are different terms and how the network is being trained to arrive at word embeddings. So for that, I will just quickly jump over to an Excel document. Okay. So let us say we are taking up a Skipgram model, right, to find out the word embeddings. So how the Skipgram model works at a high level, if you see, I have just mentioned here, you are giving input as a target words, you are deriving output as context word. So what does that exactly mean? And the other question is Skipgram model an unsupervised model or a supervised model? So to answer all that question, let's take an example. Right, just follow me carefully over here. Skipgram model is actually an semi-supervised model, sort of, because in unsupervised model, you probably will not have any labels. But in case of supervised, you will have all the labels. But semi-supervised, but I would classify this as semi-supervised because you have the labels. But only thing is that we are not labeling it out, but the system or the input itself is having the designated labels. So we are taking the labels from the inputs. So this is sort of a semi-supervised learning. How the Skipgram works, Vishal, I hope we are able to see the Excel, right? Okay. So let us say I have taken up the same example, which is I ate the orange for the breakfast. Let us say our problem statement is we are feeding in this particular sentence. We want the meaningful word embeddings for this sentence. Okay. So what Skipgram does is, if you want to implement a Skipgram model, we need to actually determine the window size. So what is exactly the window size? Let us say I take a window size of 3. Okay. So what it will do is it will take 3 words, right? So what it will do is, let us say you have a pointer, it navigates starting from here, it will move on here, here, so that it covers the entire corpus. So the pointer first takes this specific window, right? And if you take this specific window where we are taking in 3 vocabularies, which is why we decided as window size 3. Once we decide window size 3, 3 vocabularies will be taken. And what is the context word and what is the target word over here? There are 2 terms. What you see in the center here is a target word. What you see here in, what you see outside here, +1 and -1 words, the preceding and the succeeding words are called context words. So this forms the window. Within the window, we are taking in target words, we are taking in the context words. Okay, so our goal is simple, right? We want the words which appear together to almost appear same in the word embedding space. So that is the brief idea, right? Because the way how the meaning is derived is nothing but the way how we use it. So if all these appear together, then it means that once you represent these things together in a meaningful way, you can make sense out of it. So that is the basic idea. And to arrive at an idea, Skipgram model takes in a window wherein now we have selected a window size of 3. And if I select this particular word, size, this particular part of the sentence, I would generate first bigrams out of it. So there are 2 bigrams that you can generate. The target will be fixed when the context changes. That is, I generate 8 and I, the target followed by the context, then again 8 and the target followed by the context, right? So now again, I will take in the first example, which is 8 and I. So I will feed into the Skipgram network. So Skipgram network, as far as of the way how we are using in the coding, is just a plain black box model, which it is already implemented by Gensim. But I will explain you here how in general Skipgram model works. So Skipgram model is nothing but a 2-layer neural network, right? And what we want as output of this network is the word embeddings, nothing but the weights which are learned by means of training. So how the training occurs, we actually want to feed the input as the target word. We want to get the output as the context word. Okay, so okay, so this is the target word and this is the context word. So for us, we'll take this particular specific bigram 8 and I, and 8 is the input target word over here, and I is the context word over here, which is our desired output. So how do we feed in 8, and then how are we going to get I, right? So what we basically do is first we have this input 1-hot vector. So we always feed in the 1-hot representation of the vocabulary as an input, and let us say we have 2-layer network, right? So we have the first layer wherein let us say we want the output to be 2 dimensions. We want the word embedding to be a 2-dimensional word embedding. So we are giving in first layer with specific weights. So the first layer will do nothing but as a normal lookup, because we are just feeding in the 1-hot vector, and it looks up the different weights. The weights are initialized randomly, looks up the different weights and pick up the weights and then feed that as an output. So the output of the layer 1 will be nothing but the weights that has been provided by the network. Depending on the position of the 1 over here, the weights will be selected. So once you get an output, this is again being fed into the second layer. In the second layer also, we would maintain weights which are initialized very randomly. So what you see here is a different set of weights that I have initialized just for this training purpose. And what you get as an output is the dot product of this output of the first layer and the weights in the second layer. So these are the different values that you get as a dot product output for each of these different set of weights which are there in the second layer. So once you get a soft dot product, what you do is you take a softmax probability out of it. So I have computed the softmax probability for each of the values, and this is how the value comes up. If you sum it up, it will become 1. right? So that is primarily the softmax probability. And once you have the softmax probability, you can actually find out by which question stands for 1 and which question stands for 0, which is being mentioned over here. So if you see here, the highest value is given 1 and the rest of all are 0, because we want just only one word as an output. So basically what it means is you give input as age, and there is a neuron which got fired over here. You will have one neuron for each of the vocab words probably. So there is a neuron which fired over here. And what is the specific neuron? If you see, you actually see that orange is getting fired, right? Which means it actually throws in orange as an output. But what is our desired output? We want I as an output, right? So this is I. We want to feed in 8, we want I as an output. Rather, this particular, at the first instance of training, it has given orange as an output, right? And this is our desired output, wherein I want 10000, one hot representation of I, which this is what I want, but what I got is this, right? So there is an error over here. So what I need to do is I will have to apply a cross entropy loss, or I will use a loss function over here. And I take the loss function and I will calculate the loss, and then I will use the back propagation. Based on the back propagation, the weights will be the back propagated errors will be sent back to the network, and the weights will be adjusted till we predict I as an output. So this is how a skipgram in general works, right? So the same thing I have represented over here as a network, wherein you're feeding one hot vector. In the first embedding, you get an embedding which is nothing but weights, which is a lookup, and you will have again another dot product, and the output has a softmax probability. Then you would actually compute what is your one hot vector output. So what you want is actually the probability, what you are trying to maximize is probability that you get a context given a target weight. So this is a general way how skipgram word embedding is derived, and with the same with the way how it predicts, with the way how this layer networking works, right? It also brings in its own problem. For instance, let us say you have got some 100 or 1000 words in your vocabulary, and if you have to follow this method, right, every time when we have to use this specific network for training, every time we would get a different output, and whenever we have a wrong output, probably when we need to correct it, so we need to update the weights. So we'll end up updating weights for weight parameters for all the vocabularies which are not correct, right? So, and even for the ones which are correct as well. So you will end up training lots of parameters, right, which is going to be computationally very expensive. In order to avoid that problem, the algorithm actually comes up with a different technique, which is a negative sampling technique. So why we go for negative sampling? Because it is to minimize the computation of softmax. Because for softmax we have to compute this dot product, and then we have to adjust the weights for all the vocabularies, which is going to be very computationally expensive. So how do we convert this specific problem into a negative sampling problem? In the negative sampling problem, what we do is we will try to take a dot product, and then we will make sure that the dot product of the related weights are higher compared with the dot product of words which are not related. Okay, so how do we explain this? How do I explain this network? Again, I'm taking the same example. I will take in the same inputs, right? 8 and I, the bigram. So these are the inputs I give. Initially, if you see this skipgram model, I gave I8 as an input, and I wanted to get I as an output. Whereas in this negative sampling model, I feed in both the inputs, 8 and I, the bigram, and we want actually the dot product of this to be higher. So why do we want this dot product of this to be higher? And when the dot product will be higher? When the dot products will be higher when they are very closely located in the vector space, correct? So we want all this to occur together in the embedding space. So we want this dot product to be higher. So how do we do it? When we do a negative sampling, we actually, instead of using a softmax, we use a sigmoid layer. Sigmoid layer will give you an output of 1 if it is greater than 0.5, and probably it will give you 0 if it is less than 0.5. Right? We would have learned it in the logistic regression. So what happens? Let us say we take a proper input. So in the negative sampling, there are two things that one thing that you need to consider. You will feed in a right set of values. You will actually do a wrong set of values. So you will take some 5 to 6 samples probably wherein the words don't occur with the specific word. For instance, I give at once time I will give input of I8 and I, which is a right word occurrence in our text corpus, and other time I will give words which don't occur together. For instance, 8 and word are the words which are not related to the target word. So once I give this, I represent this as one hot encoding. And when I get into the embedding layer over here, I will pick up the specific weights, which are nothing but a lookup. So I will select the relevant weights based on the input one hot vector. And once I get the weights, I will do a dot product. So I have just done a dot product by myself. And if you see, there's a dot product of it is 0.44 for these two. And if you do a dot product and if you take a sigmoid output of this, it will actually give you 0, whereas we actually want it to be 1. So what you want is, because these two words occur together, we want the dot product to be 1. We want the output to be 1 and not 0, whereas the sigmoid predicts 0 because the dot product is 0.44, which is less than 0.5, which is the criteria selected by sigmoid. So what we do is, in order to make this 1, we have to go do a back propagation and adjust the weights of this network. Simultaneously, we will train the non-related words as well. For instance, we will take in the sample of words which don't occur with the target word. We will take in the one hot vector. Then we will actually adjust. And if you see that I have just given some sample values. For example, I have taken a dot product, and once I take a dot product, probably this gives an output of 1, whereas the desired output is 0. So I need to go back and adjust the weight. So by this method, right, you will not be actually running into the problem of computing or adjusting weights for each and every vocabulary. Rather, we will be only adjusting the weights for only those relevant vocabularies, right? In this way, the expensive computation problem for softmax is taken off, and we substitute it with negative sampling, wherein we get the desired outputs. So this is the basic concept of Skipgram model along with negative sampling technique. So I hope at this stage you are able to make sense of what target words mean, what context word mean, and how a Skipgram model is able to actually predict the right context based on our target vectors, right? So this is the training of this network may involve a lot of epochs, but what I saw in here is a simple computation by hand as to how this network actually functions at a single training instance. Okay, so we have not actually got into the problem. The problem for us, as we discussed, is we need to do a part of speech tagging for the given corpus, right? So I have just briefly explained over here. I mean, I have just given a brief note over here. What is that corpus that we take for training the words and embedding and giving a nice word embeddings, and also what is the corpus that we take and how do we do the tagging. So if you see here, right, I have taken a brown corpus which is available in NLTK library. The brown sample is nothing but a Brown University standard corpus technique, which is compiled in 1960, and then this probably is distributed. It has got around 15 genres. and this has got a lot of different genres, and we can actually get a lot of different sentences belonging to these genres. Those are clubbed together as brown corpus. So this is my 1 minute. I'll just display my code. Okay, so I'll just switch between the code and the presentation so that you can just a minute, please. Okay. So here, if you see, I have downloaded the brown corpus, and I have actually just displayed shown you a sample of sentences, how it comes, what are the different categories the specific corpus belongs to, and this is the word frequency distribution. The frequency distribution will tell you actually the number of occurrences of each of the words in the corpus, right? It has got probably 1 million words, so I haven't picked up all the genres. It's still okay. So these are some general, I mean, I have done a conditional frequency distribution to show you actually, you can use that to display the kind of, in a tabular format for each of the genres, what are the different number of words which comes up, right? If you're really interested, you can explore a lot using the NLTK functionalities. And this is the number of unique words which are present in the corpus. Right. So what we are going to do is we are going to take up this specific set of corpus, which is the specific set of these vocabularies. Right. Remember, these include the vocabularies which are repeated multiple times over the sentences. So what we will do is we will feed in these sentences, I mean this entire brown corpus, into our word to vector model. Right, and once we feed into the word to vector model, what we will get as an output is a nice word embeddings, which I have also shown you how to visualize using a low dimensional representation. These are the specific parameters that you see as in what we have to feed in our word to vector model. So this is the input sentences, this is the dimension that you want as an output. I have selected 300. People go between 100 and 300, so 300 is preferred. This is an hyperparameter which is already set up, and I just use 300 dimensions, hoping that it will work best. And as I said, I explained, this is the window which you want to pick it up to perform and arrive at your word representation. Minimum count will actually tell you, let us say, only if a word occurs for more than 5 times in the entire corpus, you want to do a word embedding, otherwise you ignore. So it's a kind of limiting the words which aren't occurring frequently or which are very rare. Right, negative is nothing but a negative sample. Right, I explained this technique where we do give a negative sample to reduce the computational cost for softmax probability. So if we give negative 15, it means that there will be some 15 negative pairs that will be combined along with the target word to actually perform the negative sampling. And it does, and I hope for like 10 different times, and this is to achieve the parallel processing. And one thing you have to make sure you use is SG equal to 1, because by default I believe it comes up with the SG equal to 0. SG stands for Skipgram. If SG is equal to 0, then we use the other technique, which is continuous bag of words. So if you specify SG equal to 1, you actually this will train using Skipgram model. So the rest of here I have just saved the model, I have loaded the model, and I am just displaying here the unique vocabularies. So it gives you what Skipgram does is, once you run the word to vector, correct? It actually goes through the entire vocabulary. It takes in the unique words, and then it builds at a first pass. It builds up a nice data dictionary with all the unique vocabularies and also the conditions as per our input, such as if minimal count is 5, it will just eliminate all other words. I mean, keep only the words which are required. So, and then it assigns an index to each of the words. Right. So what you see here is a vocabulary word along with an index. We haven't gotten into. I haven't displayed you the word vector yet. So just scrolling down. Give me a minute. Okay, and finally, this is how your this is the output shape, which wherein this is wherein if we take in the vectors and if we display the shape, right, it gives you 15173, 300, wherein we are down a 300 dimensional embedding for 15,173 words. So why 15,173? Because as I said, it takes in only the unique words and does a word embedding for that. If you see here, originally we have 1161192 words. In the entire corpora, it is converted into 15173 unique words with 300 dimensional representation. And if you use this dot vectors functionality, you actually get the words. You actually get the vector representation of each of the words. So what you see here is this is an array of vectors, and each vector represents a specific word. Okay, so one thing that we may have to understand here is I am just directly using this particular functionality, right? That is word underscore vectors. Word underscore vectors is nothing but a keyed vector. Keyed vector is nothing but only the vector representation of the original model and not the model itself, right? So what will happen once you train the model? You will have a model, right? You can using that specific model, which is very huge. You can use either that for computation, or you can just only take the word vectors, which is the representation over here, and use that for further computation, right? Unless you want to add a new word and train again, you need not use the model. You can actually take in the keyed vectors, which is a simpler representation, and memory wise it will take only less, because what you have is only the vectors over here, and then you can use it for further processing. For instance, using the keyed vectors over here, which are the word vectors, I can actually apply these functionalities, which are similar by word. If I give Saturday, it gives me the most similar words to Saturday, which are like Sunday, Friday, Wednesday, and all. So what you see here is a cosine similarity, or the cosine similarity. The value here tells that with reference to the input query Saturday, these are the closest words which occur. Sunday, Friday, Wednesday. So with reference to the word money, gives you cloth, repay, unemployment. With respect to child, gives you teacher, autistic, temper. So what it means is these are the words which are closely related to the input words. Child. So which means that these are embedded, these are closely represented in the word embedding space. And here I have just displayed the word vector for child. You can see a 300 dimension embedding for the specific word. So what we would do further is also I am taking that input. So I have just taken only 1000 words from the input text, and I am just representing that in a two-dimensional representation. So I am using TSNA, which is a T-distributed stochastic neighborhood embedding, for visualizing it in lower dimensions. So I use just 2 dimensions on only 1000 vocabularies, and what you see here is a data frame table with the lower dimensions from TSNE. So these are the different lower dimension representation for each of the first 1000 words. And what I show you here is the lower dimension representation of those 1000 vocabularies. You can see that the colors which are together are actually clustered together. This is a scatter plot, and here is a scatter plot with the annotation wherein we are actually pointing out what are the different words as well. You see, like, you are not able to make any sense of it because they're all closely clustered together, and the words are also overlaid on top of each other. Okay, so what I am going to do further rate is I'm going to take another corpus, which is kernel 2000 corpus, and what is corpus will have is this is how the corpus has a set of vocabulary and the corresponding taggings already done. So what we are going to do is we are going to use that corpus. We are going to use this word embedding, and finally what we are going to do is we'll train this. We'll build a neural network architecture to train the network with these particular tags, the word and the tags, and correspondingly we will test it out to see how our network is determining the tags, the POS tags. So what you see here is the input is nothing but the vocabulary and the corresponding tags, which are already done and are present in the kernel 2000 tags corpus. So okay, so there are a lot of different functions that I use to actually arrive at this POS tags. So I have just drawn here a flow chart, how the flow works, because if you go into the code, right, there are a lot of different functions I use, which may find it a bit intimidating to relate each of them. So to understand and make it better, I have drawn a flow chart over here, which will give you, which will probably help you to visualize better how it is being done, right? So what we have already is we already have the word embedding matrix, or nothing but the word vectors which have come out of the brown corpus, correct? Using the Skipgram model. So what I show here is whatever I highlighted in yellow or the amber or the functions. So get int data is one function which I'm using. Get tag vocabulary is another function that I'm using in this code. Add new word is another function that I am using. So how am I using all these functions and getting the tags? So what we have to do is, right, so we have the word embeddings available, correct, and we also have an input data set which is in this specific form, right? So first step what we have to do is convert this into the unique words, sorry, convert this into the numbers, because all we need is a number representation, right? And we have to convert the tags as well to numbers so that we can feed into the system. So that is being primarily done as a part of this function. For instance, tag to ID is tagged words, and word to ID is fed in as an input to get in data function, which is specified over here. And what you get as an output is the words mapped to the corresponding unique IDs, the tags mapped to the corresponding unique IDs. So how this function really works is word to ID is nothing but the mapping of the word vector, the words, the vocabulary, each of the vocabularies to the specific IDs. So once it takes in the input data set, it actually checks whether the specific words are present in this particular array or dictionary. If the word is present, what we need is just to get the corresponding word IDs, right? And there is also another case where the word need not be present. The words that we feed in as an input from kernel 2000 data set is not present in our word to IDs, because word to IDs are primarily composed of the vocabularies which are trained from bound corpus. So how do you handle the words, and how do you assign a unique index or integers or representation for the words which are not actually present in the corpus? So for my model here, the way how we have handled is I have treated every word which is not present in the corpus as an unknown word. So once for all those unknown words are handled differently, for instance, for unknown words, we actually make that word as an index 0, and I use the token UNK to actually point to those words which are unknown words. and the word vector representation for the unknown words is actually taken as the mean vector from all the embedding matrix. So what I do is, from the word vector, right, we have this 300 dimension word vector representation. I take a mean of it, and that mean is what I consider it as the vector representation of an unknown word, and I push this new unknown word as well as a new word into the words to ID dictionary. So whenever a new word which is not there in corpus comes up, it will actually go and then tag it as an unknown word. It will identify the relevant index as 0. Also, it will take the POS tag as well as 0, depending on what we want to set it up, and no, depending on what the POS tag is. Simultaneously it goes and updates the word to ID dictionary to specify that we have encoded an unknown word, and this word has to be updated over here. So it performs these specific functionalities, and then it actually I have also printed out the unknown words that we encounter. As long as the unknown words that encounter is very less, we don't have to worry much, because accuracy is not being much impacted. So I have just printed out here the unknown words. There are like around 0.4143 percentage, and then in the training data set, and then 0.149 percentage in the testing data set. So very less unknown words, because because the brown corpus that we used for word embedding has got a rich vocabulary, which is present, which almost all the words are there in Cornell 2000 dataset. Okay, so now what next? Once we get the output, right, which is the word ID and the tag ID, the corresponding values for word and the corresponding values for a tag, that is being fed into the input as the network that is being built in the next set of functionalities. So here is where I have defined the model. So we now next step is, once we are done with our input, right, what we have built up is a network which has this particular structure. We first have I used Keras, which has an embedding layer in the beginning, followed by a flattening layer, followed by 2 dense layer network, and a softmax activation. Right, softmax activation. So how this network functions is, there are 2 different architectures that I have utilized. One is context independent, other one is context dependent. So what exactly is the difference? So now if you see here, right, first I will show you the context independent model. Next I will show you the context dependent model. So this is how the model is defined. We are using a sequential model. I am adding an input embedding layer, and I have given the input embedding layer with input dimensionality, output dimension as 300, and I am using the weights as the embedding matrix weights, which we have got as an output of word to vector, right? And then I have used input length as 1. So input length as 1 will actually tell me how many words in context this embedding layer will look at. So right now it will just take only 1 word. It will consider each and every word as independent, and then it will build up the embeddings, right? So what this embedding layer does, it actually again performs the same word embedding based on the original embeddings. It will use as an input weight. It will take in these vocabs that we have taken up as an input. It will also use the weights which are arrived as part of the original word to vector, and it will again give up an updated embedding for our current data set. So this is how we have done a flattening. We have added a flattened layer, then we have a dense layer with tan H activation, and we have another dense layer added with softmax activation. And the optimizer I have used is Adam. The loss is the cartographical cross entropy, and the metrics is accuracy. I want to determine the accuracy of this entire finding, or the entire computation. So so this is what happens once you feed in the words, right? The input tags input, which is in the form of the words. Okay, so there is one mistake over here. Okay. So once you feed in the words and the corresponding tags, right? What will happen here is the network will get trained. It goes by embedding matrix. The embedding gets updated, and once the embedding gets updated, the embedding matrix is the input. The embedding matrix gets updated. The output is being flattened, fed into the dense network, and we have a two-layer dense network over here. With one with 50 neural networks, and the other one with Softmax has got, sorry, the other one output has got 44 network, 44 as classes, different set of tags are there. So we have 44 different neural nets as an output. So that is how the network is built, and the parameters here actually tells you how many different set of weights are being activated or has to be trained. So if you see over here, for each of the vocabulary, there are around like 300 dimensional matrix, so we have 300 weights. So these many parameters are being updated, and for each of the dense layers, let us say this is given as an input, we have 15,050, depending upon the size of the neural network, depending on the size number of neurons which are there. The same thing opens for dense to layer, and this is being fed as an output. And once you get an output, probably you will get a specific tag as an output. And once you decide that the tag is right or wrong, depending upon that, you will actually do a back propagation, and based on the back propagation, the weights will get updated, and you will get the corresponding and the corresponding training will happen. So that is what being handled in this specific model, and this is how it is. And the next one is I have written out the functions to actually evaluate the model as well, and this is how the training happens. Once you fit the model with the specific, I have used the batch size of 128 and the neural network size of 50. Just only one epoch with the loss of 0.676 and an accuracy of 0.77. This is just for training, and if you run the same network if you use that model for testing, the trained model for testing, which is the context independent model testing, here we get an accuracy of 0.80. Which is what I have mentioned over here. So this is how the neural network architecture training happens. So you basically feed in the input of the Cornell 2000 data set, use the embedding layer with the embedding matrix built from word to vector, then flatten it, pass it onto the two fully connected layer, and use the softmax optimization to get an output, and do a back propagation to actually improve the to make changes in the weights. Now you see here the accuracy is 0.8, correct? So for us to improve the accuracy, there is a context dependent model also which we have built. The context dependent model is nothing but when we are actually doing the embedding. Right. So what we have done is I have taken the total context, which is like around 5 words. So input underscore length is decided as 5. So what will happen? It will actually take all the words in the sequence, and then it will start performing the embedding rather than looking at each of the words as an independent words. So that's the only change. So once we do that, right, again it will go through the same process of using the embedding matrix, updating the embedding matrix, providing the right embeddings, then get into the flattening layer, get into the two dense layers network, and a softmax output with the Adam optimizer and categorical cross entropy loss. So finally, with this particular model, right, once we train the model, once we train it, and we use that for testing, the way when we evaluate, the loss for it has actually reduced and the accuracy has improved to 0.9. That is what I have mentioned over here. The loss has reduced and the accuracy has improved, and I think primarily because the embedding would have been better now since we are doing a context dependent model, and the accuracy has actually increased 10%. If you see from here to there, it's from 0.8, it has actually gone to 0.9. So So in a way, what we have done is we have now taken in a big corpus set of Cornell 2011 datasets. We have trained it using the tags, and then we have actually derived the tags for the different vocabularies which are there as part of Cornell 2000 dataset. So this comes back to our original problem. We want to identify the part of speech tags for the given corpus. So what we did, we created a word embedding matrix using the Skipgram. We trained the new dense neural network, the neural network architecture that we built, wherein we updated the embedding matrix followed by the classification. Then we did a tag testing, measured the accuracy. Then we again just modified the neural network architecture by building a context sensitive model, wherein I updated the input length to 5, which will take all the context, all the sequential context, and then perform a better embedding, thereby leading into the better results. Okay, so this is how we have actually utilized the word embedding from Skipgram model and used this as an embedding to derive, use this as an input for a network architecture to actually derive the POS, the part of speech tag for the given corpus. So the coding, the code is available in the GitHub page, where the link of which I have given it over here, and the detailed, the functional block diagram will actually tell you how the function is being utilized in order to process the input word and map it with the corresponding POS tags, and how to handle the unknown tags. Okay.
So that's about it.
Yes, Vishal. Yeah.
Okay. So audience, any questions? I am not seeing questions coming on this presentation. So Ramesh has been very good at presentations before. Also, we don't see many questions, but I think that is because his explanations are very good. Either give me feedback or give me questions, so I know we know what's going on in audience mind here.
Yeah, and if you feel that there is really a lot of concepts over here, yeah, I mean, it is. I tried my best to explain in detail about the Skipgram calculation, and also those could be really overwhelming if we have to listen and understand in one session. But you can actually go back and then go through this once again to understand the sequence and how we have done this coding.
Right. So for everybody's convenience, I am putting in the self-study YouTube link where it will be posted in 2-3 days time. So I shared the self-study YouTube link where it will be shared in 2-3 days time. Meanwhile, one question has come. Can you please explain how content-based Skipgram works?
Can you please explain how?
How content-based Skipgram works?
Okay, so if you are talking about Skipgram, are we talking about continuous bag of words, or we are talking about the context-dependent model? So
I'll request the gentleman to please elaborate. Are you talking about the continuous bag of words? The context-dependent model is what he's asking.
okay. So the primary difference between the context-independent and the context-dependent models are in terms of using the input length as a parameter in the embedding layer. So what would happen is once we get into the embedding layer, right, it actually looks for building a better word embeddings based on the input. So when we are trying to build the embeddings, this context dependent model, what it does is we have fed in the length of 5, right? So it takes in 5 words at a sequence, and then it tries to build the context. So in this way, you see the output. You see the output step of here is 1 into 300, which is like you give one word and then you get a 300 dimension output. Whereas if you see here in the context dependent, it takes in 5 words and then it gives an output 5 words with 300 dimension output. So once it starts looking in the sequence of words as a context, it starts building a better embedding, and from the better embedding you get better results which can be visualized from accuracy. So that's the primary difference in the independent and dependent model.
Thanks. So any other questions, audience? So since I'm not seeing any more questions coming in, we would like to close it here. So thank you, Ramesh, for presenting. And we are dot on time, just 5 minutes ahead, but pretty good presentation, I would say. So another follow-up question has come. So as you explained 5 words, it's the batch data.
It's not exactly. If we are talking about the batch, actually, what I'll just show you in the code. Batch size will actually tell you how many words or the sentences you want to pass it as a part of your training. This is not a batch data. This is just an input data for the embedding layer. So if you see here, right, in the embedding layer, we have an input length. Right, in input length, we are actually going to feed in that specific window size what we want to give us an input to, and this is the this is what I mentioned as the sequential words to make the embedding. Whereas if you want to use, if you're talking about the batch size is nothing but the just a second.
So Ramesh, he's saying, are we not using any particular sequence like we do in RNN or LSTM?
Sorry, Vishal, can you repeat that question?
So he's saying we are not using any particular sequence like we do in RNN or LSTM.
If you're talking about sequence, yes, in the context dependent model, the sequence is being used, which is why we have given an input length of 5 to arrive at the context. And in the case of context independent model over here, we are not really considering the sequence. So here we're just looking each and every word as an independent word, whereas here we are looking a sequence of 5 words and arrive at an embedding.
Okay. So I think that's about it. So thank you for all the answers and presentation, and thank you audience for joining. Look forward to see you in future webinars. Thank you. Have a good night.
Thank you. Thank you. Thank you, Vishal. Thank you.